Okay, now we're official. Okay, before we get started, anybody have any questions or any concerns? The reading assignment last week was just basically an introduction.
Hi, this is Ed. I just had a quick question about, I already have a call sign, but
Uh-huh.
it's from Colorado. So now that I moved up to Idaho, do I need to get a different call sign?
Well, in past years, that was the case, but they've discontinued that now. So now, no matter where you live in the country, you just take your call sign with you.
Oh, okay. Thank you.
It was getting to be too much of a burden for the FCC, so they said, well, let's just stop this. So, yeah, once you get your call sign, you can take it anywhere you want.
Nice. Thanks.
Okay, and also what I'm gonna do is mute everybody as soon as I can find it. I think most everybody is. Let's see. There. So anyway, if you check and make sure that your microphone is muted, and
Yes.
then and if you would like to talk, you just push the space bar, and that acts like a press to talk switch. So that way we don't pick up any background noise or any additional conversations. So it looks like everybody is.
Dale, I have a question on the FRN number.
Yes, uh-huh.
I went back into the FCC site, and since I took your class last time, and it was still there and I could still sign in, but it said it was only good for a year. Is that what you remember?
Well, I think what they do is if you don't use it within a year, they'll cancel it. But once you use it, then it'll be good for, as long as you're using it. So you have basically 1 year to get your license under that FRN number. And if it takes more than a year, then you'll probably have to reapply for another FRN.
Okay, so when you say use it, does that mean signing in using that number with the FCC?
No,
Starts the
actually,
year all over?
no, what it means is when you get your license, so your FRN number, that's basically your account. And when your license comes through, it will go into your account under your FRN number. So once you have a license there, then your FRN will stay as long as you have a license. But what they're doing is once you've created an FRN number, and if you don't ever put a license in it, then they cancel it after a year.
Okay, I didn't see a way to extend it, so I know that we're getting close to that. Okay, thank you.
Okay, you're welcome.
Dale, I also know on that if you are taking classes and you do not have a license, that number has to be used for FEMA and other tests, and so it'll continue to be active if you're using it for other purposes.
Oh, okay. Yeah, as long as you're using it for something, they'll keep it active. But basically what they do is they do house cleaning once in a while, and any FRNs that aren't being used, they cancel them just so they don't have a lot of dead space out there.
Okay, so here's the workaround.
Okay.
Simply apply for your GMRS license, pay your
Uh-huh.
$10 or $35 or whatever it is.
Yeah.
Get your license, and then you have your FRM tied to a license.
Right.
You're
Uh-huh.
good to go.
And actually, for anybody that'd like to get your GMRS license, it's really easy to do. Just go ahead and fill out the application, costs $35, and you'll get a license there. So a lot of people have both. I have both GMRS and a ham radio, and you can certainly do that. And both of them will go under the same FRN number because that account belongs to you. So any licenses that you have will go under your FRN number. So yeah, if you're concerned about it, just go ahead and apply for a GMRS license and then put that in there. Then you'll have both. Okay, so was everybody else able to get your FRN number set up? I know the FCC webpage is kind of difficult to navigate sometimes. Um, And sometimes you have to kind of poke around to find what you're looking for. So if you haven't been able to do it yet, I would really encourage you to go ahead and get your FRN number, get your account set up. And then, like I say, you've got a whole year to get your license. And if you don't get your ham radio license, then you can go ahead and get a GMRS license. Okay, so Chris, you got yours. Good job. Okay, well, so today we're actually going to start getting into some of the meat of the subject. So, oh, I didn't get that set up. Hold on just a minute here. I wasn't as prepared as I thought I was.
Hey Dale,
Yes.
I have a quickie link for the GMRS license if you want me to throw that up in the chat.
Okay, sure.
Okay, it's up.
Okay, thank you.
Hey Dale, just a quick note. I just threw the link up to get the GMRS license through the FCC.
Oh,
So if
okay.
anybody wants to go on there, so I did that as well, along with
Okay.
Scott.
Well, thank you. Okay, now I think I'm ready, finally. Oh my goodness, we got 8 more people checking in. Okay, hold on just a second here.
Hey Dale, when you're done, what repeater are you on? Like your GMRS repeater?
Mine is GMRS channel 17.
Okay, thank you. I'll try to see if I can find it on my stuff.
Okay. Okay, hopefully we've got everybody logged in. Let's see, this and this. Okay, can everybody see that okay?
Yeah,
Okay, so tonight we're going to start with the very basics, and we're going to talk about electricity, just basic electricity. What is electricity? Where does it come from? How do we make it, and what we can do with it? And once we have a basic understanding of just basic electricity, it might make it a little easier to understand the things that follow. Okay, if you go back in your memory when you were probably in school, maybe high school or even grade school, when you talked about atoms, everything on this earth is made up of atoms, and there's lots of different kinds of atoms. And an atom has 3 parts. There's the neutron and the proton, which makes up the nucleus, and then the electron. And the electron spins around the nucleus, around the outside.
then you
And
have
the
an atom vessel.
Yeah. And the electrons actually travel at the speed of light, 300 million meters per second. And if you think about how tiny those are, that's a that's really spinning pretty fast. So anyway, we're going to talk a lot about electrons, and I've got a video. Whoops, I'm sorry. Okay, this is see, in that previous example, this just shows 3 electrons here, but some atoms have quite a few. Some of them have more than 100 electrons. And then, okay, so let me go into the video here. I wish there was a better way to switch back and forth, but it's kind of cumbersome. Oops. That close all these applications so I can get to it. Now I'm going to show you a video. Some of these parts I've pre-recorded because it's very difficult to try to demonstrate over Zoom. And the videos work really good, except that the guy who was doing it obviously wasn't professional. I mean, he's a young kid, and I really appreciate it. But so the videos aren't the best, but hopefully we'll be able to get the point across. There we go. Okay, so this is our first video here. Okay, can you see that okay?
They're made of protons, neutrons, and electrons.
Okay, very good. Now, protons, neutrons, and electrons. Now, what's unique about the electrons? What are they doing?
That is not unique about the electrons.
Remember how the electrons are spinning around the nucleus?
Oh yeah, those ones.
Yeah, okay.
I keep forgetting. It's been a couple.
Yeah. Yeah, so they do spin around the nucleus. Now, here's a kind of a trick question. Can you take an electron away from an atom? Kinda. You can, but and typically what will happen is if you take an electron, and what I'm doing is we're going to pretend this is a piece of wire here. Each one of you is an atom, and I've given you 1 electron. Now, real atoms have more than one, but we don't want to do a juggling act here. So if I take an electron away from an atom, that atom will then steal an electron from the atom next to him, and then keep going down the line. Now, if I take this extra electron and give it to this atom here, and if you have an extra one, you pass the extra one along. Okay? Okay? So, when I took this electron here and moved it over here, what happened to all the electrons in the circuit? They all moved, didn't they? Now, if I continue doing this, if I keep taking one from here and move it over to here, and then you keep passing them around, and if I keep doing this, what's happening to the electrons in the circle? Okay? And just keep passing them on. Okay, so the electrons in the circle are all moving. Now, these moving electrons is called electricity. Now, we didn't create the electrons. All we did is we took electrons that were already here and we made them move. And by moving those electrons, that's what electricity is. Okay? So it's actually a pretty simple concept. So what I'm going to do is we're going to go back inside now and we're going to show you how we actually do that and how we create electricity and some of the things we can do with electricity. Okay? So we'll move back inside and
You want us to collect this?
Okay, that was kind of a short one. Come on. There we go. Okay, so what we're gonna do is we have atoms, everything that's made up of on this earth is made up of atoms, and we can actually cause these electrons to move, and those moving electrons becomes electricity. And I've got another video here. I'm going to show it to you. This is going to demonstrate how we actually do that. Let's see. I have to go find the right. Okay, so this is the second video. I probably should have put those two together. Okay, here we go.
Okay, now we're back inside. And what I have here, this is a piece of wire, it's a piece of copper wire. And copper is made up of electrons. Made up of atoms. I'll get it right yet. And atoms have electrons. So we have electrons in this piece of wire, right? Now, do we have electricity here? No electricity, is there? Because the electrons are not moving. They're just staying in one spot. So if we can take some of these electrons in this wire and make them move, then we can actually create some electricity. So let's take the wire. We're just going to coil it up here. And now this is a meter that will actually measure electricity. So I'm going to hook this little piece of wire up here. And we have found the unique thing about electrons is that they're actually magnetic. Okay, so I'm going to turn this meter around. I'll turn it so everybody can see it. So what I have here, this is a magnet, and this is just a piece of wire. And I'm not actually going to touch the wire, but I'm going to pass the magnet over the top of the wire and look and see if we get any electricity there. Can you see it? Okay, can everybody see it? You guys see it over there? So all I'm doing is just taking this magnet, and just passing it over the wire, and we can actually cause those electrons to move. And so we're creating electricity. And that's how simple it is, just a piece of wire and a magnet. Now, what do you think we can do to get more electricity? That's just a very, very tiny bit there. How about if we get a bigger piece of wire? Oh, I'm sorry, what?
Sometimes if you are low on electricity, you can get it from anything. As in, you can get it from water if it's moving fast enough. You can get it from friction if it's moving fast enough. And you can even get it from wind.
Yep, that's very true. Absolutely. And this case, we're going to get it from wire, piece of wire. So what I have here, this is a bigger piece of wire. There's about 50 wraps around here. And let's hook that up and see what that gives us. Let me get back here where I can see it. Okay, you get any electricity there?
Yeah.
Okay, so we got a little bit more electricity by just having more wires. And it can be, rather than having a whole bunch of little pieces of wire, we just take a single piece and we just wrap it around. So now the magnet is passing over multiple layers of wires. Okay, so let's go to a little bit bigger one here. This, I think this is about 100 or 150 wraps of wire around here. Let's hook that up and see what it does. Okay, getting a little bit more? Yeah, that's quite a bit more, isn't it? So the more wire we have, the more electricity we can get. And also if we get a bigger magnet too, that will also make more electricity. So in this case, bigger is better. Now what I have here, this is a little homemade device, and I have 4 bundles of wire with about 500 wraps of wire in each bundle. So there's a lot of wire in there. And see in the middle, I put on a little shaft, a magnet. See how we can turn the magnet inside there? And so what I'm going to do is by having this magnet pass over those wires, we can actually generate electricity. So let's hook that up and see what that gives us. Oh wow, we're overloaded. Still overloaded. There we go. Okay, see, by spinning the magnet, see the electricity that we're getting there? Now we're getting about 5-6 volts there. Okay, so every time I turn it, but it only, yeah. So so every time, now it only works when the magnet is moving. The magnet has to be moving in order to generate the electricity. Just sitting still, it doesn't do that. Okay, so let's, I'm gonna hook up a drill to it just so we can spin it a little faster. Okay, let's see what that does. Yeah, actually about 24 volts. That's quite a bit of electricity, isn't it?
Yeah, it is pretty.
So now, let's see if that really is electricity. Let's hook up a light bulb to it and see if we can actually light the light bulb. Okay. Now, get this where we can see it. So it really is electricity, isn't it? Now, the only reason this one flickers is because I didn't put the wires all the way around. I left it open so you could see inside of it. But on a real generator, the wires would be all the way around, so it's nice, smooth electricity. And this is how they actually generate electricity at a power plant. Have you ever heard the term hydroelectric? Anybody ever heard that before? Okay, hydro means water. Well, what's water got to do with electricity? What? Yeah, exactly. So what they have at a dam, let's say where they're generating electricity, is they'll have one of these, except it'll be this big around and probably that tall. They're huge. And this shaft will go way down to the bottom, and there's a propeller down there. And the water flowing through the propeller is what spins the magnet, and that's what generates the electricity. I actually got to go to the Grand Coulee Dam one time, and they were in the process of building a new generator. This part here was 30 feet wide, and the entire generator was 5 stories tall. I mean, that's huge. Yeah, they generate a lot of electricity. Here it's just a very small amount, but see, even just by turning it by hand, you can see that we're actually generating a little bit of electricity. So that's how we make electricity. It's just a very simple principle. Okay, so now that we know we're like, oh, actually, I need a helper here just for a minute. There you go, like that. Okay, now have you ever heard the term of AC power and DC power? You know the difference? Okay, let me show you the difference. Okay, AC power means it's alternating current. What does alternate mean? Yeah, it goes back and forth, doesn't it?
It goes
Okay.
like this around.
So let me show you. Now you have to hold it really straight because it tends to fall off. Now we're going to pretend that this is our wire, okay? We have 2 pieces of wire. Have you ever noticed you have to have a complete circuit? Have you ever heard that before? You have to have a complete circuit for electricity to work. So it works like this. If I'm generating the electricity and the other end is called a load, anything that uses electricity is called a load. It can be a light bulb, a refrigerator, radio, or whatever you have. If it uses electricity, it's called a load. So if I generate electricity here, you see the electrons are following along the wire and it's going through the load. Okay? So it makes a complete circuit. The electrons have to be able to go around and around and around and back to the original. Because we're not creating we're not creating the electrons, but we're just causing them to move. And so they have to be able to move in a circle. Okay? Now, if we have current that flows like this, This is called direct current, or we call it DC. You heard the term DC power? So DC means that it's just direct current. It goes from here to there and back again. It makes a complete loop. Now, what if I was to, I know it keeps falling off.
Yeah.
Okay, now what if I was to go like this and then come back and go back and back and back like this? Okay, this is called alternating current. That means the current goes back and forth and back and forth. So I'm still generating power here, and the power is getting to the other end. See the wheels moving at the other end? But it's going back and forth. It's alternating. And this is called alternating current. That's what AC means. So DC means direct current. And if you could see the electricity, it would go something like this. To stay on. So direct current would look something like this, where it just goes continuous in one direction. But alternating current goes back and forth like this. See, now I fell off. Now, anytime that you have alternating current, there's always a frequency involved with it. And what that means is how fast or how many times per second it does this. Okay? So if it goes out and back one time, that's one cycle, or we call that a hertz, H-E-R-T-Z. So it's 1 hertz. Now, if I was to go something like this, if we go 1, oh, keep it straight. There you go. Okay, 1, 2, 3, 4, 5. Okay, that's about 1 cycle per second. That would be 1 hertz. Okay? Now, if I speed it up, let's go 1, 2, 3, 4, 5. Okay, that's about 2 cycles per second. So that would be 2 hertz. Okay, and we can keep getting faster and faster and faster. And the lights, like what we use in our buildings, those are actually 60 hertz, or 60 times per second. And that's the standard power that's used in the power grid. And then we can keep going up higher and higher. We can get into the megahertz and gigahertz, and the frequency just gets higher and higher. Okay, so that's the difference between alternating current and direct current. Okay, thank you. Let's just set it right here for now. Now, I got a trick question for you. Let's go back to our generator here. Okay, remember how we're spinning the magnet here? We're turning the magnet and generating electricity. Okay, is this direct current or is this alternating current? How many think it's direct current? Okay, how many think it's alternating current? Don't be afraid. You were the only 2 that got it right. This is actually alternating current. And then you're saying, but wait a minute, the magnet's only going in one direction. How can that be alternating current? Well, let me show you. Okay, this is a picture of our magnet. Okay, our magnet right here. Now, every magnet has these lines around it. These are called lines of flux, F-L-U-X, or flux lines. And every magnet has them. Even the Earth itself has these lines of flux. Okay, now if this is our wire, and what we're going to do is we're going to pass the magnet right by the wire. And as these lines are cutting into the wire like that, it's causing the current to go that direction. Okay? So when it gets to the center, it's not cutting anymore, so it stops. Then as the lines on this side are pulling out of the wire, it causes the current to go the other direction. So each time the magnet passes, the current goes this direction, then it goes that direction. So each single pass will cause 1 cycle. You know, the current to go one direction, then the other. Okay? So it's actually alternating current. Okay, so now that we know what electricity is, I'm going to show you some things we can do with electricity. It's now the first thing, we can take this wire, remember this coil of wire that we had, and we could run current through here, electrical current, and it's going to cause 2 things to happen. It's going to cause the wire to heat up, and it's also going to create a magnetic field. Let me demonstrate that to you. What I have here, this is what we call iron filings. If you ever take a magnet out in the backyard and drag it around through the dirt, you get this black stuff that sticks to it. That's actually iron. It's powdered iron. So what we do is, if we take the magnet underneath here and see the magnetic field. Now see how it's kind of standing up there? That's those lines of flux that I was telling you about. You can actually see them in the iron. See how it just kind of stands up on edge? Okay, so a magnet, this is a way to see a magnetic field. So what I'm going to do is hook up, and I'm going to put some electrical current through this coil of wire. And if you look here, see the magnetic field? So we're actually creating that magnetic field, okay? Because it's not a magnet, it's just a coil of wire, and we're running electricity through it. Now, if I disconnect the electrical current, see the magnetic field went away. So we're actually creating that magnetic field. And it's actually starting to get warm a little bit, and it's not really super hot. But if we left it on for quite a while, it'd probably get quite hot. But you can actually see there's a magnetic field there. And by doing that, we can create all kinds of cool stuff using magnetic fields. This is called an electromagnet. It's a magnetic field that's electrically created. Okay? So what it can do, so what I have here, this is a piece of iron, and I've just wrapped a whole bunch of wire around the iron, and the wire is just hanging out the end. Now I want you to check and see if there's any magnetic field there. Use the metal there. Does it stick? No magnetic field, is there? Okay, now see if there's a magnetic field there. See, it sticks, doesn't it? Okay, that's pretty strong, huh? So we can actually create a magnet by using electricity. Here, just stick it on there and leave it. So this is stuck there, and as long as I keep the electricity going through there, the magnetic field will stay. Now, if I disconnect it, the magnetic field's gone. So we can actually create a magnet. We can turn it on and turn it off at will to make it do all kinds of cool stuff. Now, I have one other thing. Okay, that'll work. Thank you. I was actually going to demonstrate this, but I've done it so many times that I've actually wore it out. I tried to fix it this morning, but I ran out of time. What this is, I have 4 bars of iron around here, and there's a coil of wire wrapped around each one. And then on each bar, there comes out here to a connection point right here. And if I put it in here, and you see these 2 little spring-loaded things, when this rotates, it makes contact there, and it will magnetize this bar right here. And down here is a fixed magnet. It's glued in, so it won't come out. And when this is magnetized, those 2 are going to pull together. And then it disconnects, and the next one connects. This becomes magnetized, and it pulls that one together. And then the next one, and the next one, and the next one. And it'll actually spin quite fast. And that's how a motor works. That's how we do a motor. By just turning these magnets off and on very rapidly, and it will cause it to turn. What about a light bulb? You know how a light bulb works? Just a very simple light bulb? How? Yep, exactly. So inside the light bulb, there's a very thin wire. If you look close, you can actually see it. This is called a filament. And that thin wire is actually made out of carbon. So what we can do is we can pass electricity through that carbon or through that filament. And remember what we showed a little earlier? That if you pass electricity through it, it will actually get hot. And we can actually make it get really, really hot. But what we've done, well, first of all, let me ask this. In order to have a fire, you have to have 3 things. What are they?
Oxygen.
Okay, what else? Oxygen, what else? Fuel, what else?
Heat.
And heat, okay? So we know that electricity will generate heat, but inside here, we've made this a vacuum. We've taken all the oxygen out. So you can't have a fire because there's no oxygen. But we have heat and we have fuel, which is the carbon element. So we can actually create a fire inside here, but it won't actually burn because there's no oxygen in there. Okay? So let me hook up a little, this is just a small one here. Everything I have here is very low voltage so that you can't get shocked off of it. Okay, so by passing electricity through here, see the little filament in there? And it's actually heating up. And if you touch it, it starts to get hot. And if we put more electricity, it's going to get hotter and hotter and hotter, and it's going to start glowing. See how bright it's getting? I mean, it's actually a fire, but it won't burn because there's no oxygen. We took all the oxygen out of it. So we have heat and we have fuel, and the end result is we're getting light from it. And if you've ever put your hand on a light bulb, they're very, very hot. It's because it's actually a fire inside there. And eventually, someday, that filament's going to burn out, and you have to replace the light bulb. They only last so long. So that's how we have light bulbs. Now, the newer light bulbs are mostly LEDs, and that's a little different technology. Okay, so those are some of the things we can do with electricity. Now I want to show you how batteries work. Have you ever wondered how batteries worked?
Yeah.
Okay, if you want to hold that, and let's put some electrons on here. Yeah. So you're already ahead of the game. Okay. Okay, now a battery is actually made up of two metal plates. And these are going to represent, now I want you to hold that one right below that one, like that. So we're going to have two metal plates. They're going to be very close together, but they don't actually touch each other. We put some insulation between them so that they can't contact each other.
And if they do,
And-
they start to
And each one is made up of atoms which have electrons. Now, if we were to take the electrons off of this plate and put them onto this plate up here, okay, so now we have too many electrons up here. And remember we talked about earlier that atoms don't like to have more electrons than they're supposed to. So the atoms up here are rejecting these and they're pushing them away because they don't want them. And over here, these atoms are missing electrons, and they're trying to grab electrons. So on this plate here, we say that it has a positive charge because there's too many electrons. We put excess electrons in here, and this one has a negative charge because it's missing electrons. Okay, so this plate here, it has a positive charge, and this has a negative charge. So think of it like this is under pressure because there's too many electrons up here, and this is like a vacuum because there's electrons that are missing. So these electrons want to get down there really bad, but they can't because there's insulation. So if we provide a way, so like a light bulb or something, if we hook the light bulb from here to here, then the light bulb will actually allow the electrons to pass through and back to here. And as long as we have excess electrons, we can keep going and the light bulb will just keep burning. But eventually, at some point, all the electrons are going to be back where they want to be. Okay, so once the electrons are all back where they want to be, we say it's a dead battery. Doesn't mean the electrons are gone, it just means that they're all back where they want to be, and we don't have any more charge anymore. So every battery always has a positive end and a negative end. And positive means there's too many electrons, there's excess electrons. And the negative just means there's missing electrons. Okay? So let's just set that there for now. Thank you. Okay, well let me show you, have you ever wondered why a battery is round? Well, I've actually opened up a battery so you can see the insides of it. And if we unroll it there, this one's getting kind of old. I've done this a lot of times. Let's see, is it that one? Oh, actually, that's the wrong one. Okay, here's one. See, if you unroll this, see, there's one of the metal plates right there. And then inside, there's another metal plate. See that one right there? So there's two metal plates inside the battery, and they're rolled up together. Now this white stuff, it kind of looks like cotton. That's actually that insulation I was telling you about. We call that a dielectric, and that's what keeps the plates from touching each other. But these two plates, we can make one of them a positive charge. We can put extra electrons on it. And the other one has a negative charge because we've taken electrons off of it. And then we keep them insulated. Now there's also some chemistry involved. When they actually build the battery, they put some chemicals in there to make it work better. Because the plates, when they're dry, it works, but not very well. But with the chemistry in there, they work a lot better. So that's the reason why batteries are round. They just have these two. If you unroll it, it's probably about that long. And they just roll them all up together. And you can see these batteries here. You can see they're all rolled up in there. And one of those, like if we have a, oh, here we go. If we have a battery here, one of these ends is connected to the negatively charged plate, and the other end is connected to the positive charge. So there's our two contacts, one on each end. And one end is a positive and one end is a negative. Okay? Now there's different kinds of batteries. This is an actual carbon battery. These are the kind you get at the dollar store. They're not very good, but you know they'll last for a little while. And basically it has a zinc rod in the middle, and there's carbon, dry carbon that's packed around. And the zinc rod acts as one plate and the dry carbon acts as the other. So you can take electrons from one and charge up the other. These work pretty good, but they just don't last very long. They're kind of the cheapy ones. Have you ever looked inside of a 9-volt battery? How do they get 9 volts in that little box? Well, if you open it up, and inside there are actually 6 little tiny batteries, very small. And batteries, batteries are always 1.5 volts. Each one, this produces 1.5 volts. If you want more voltage, then you can just stack the batteries together. Like here, I actually have 2 batteries in here. So if this is 1.5 volts and this is 1.5 volts, by putting them together, I can actually get 3 volts out of it. And by adding another battery, we can put 4.5 volts, and we can keep stacking them up and get however much voltage we want. So in here, if we have 6 of these, and each one's 1.5 volts, so 6 times 1.5 is 9 volts. So that's how we get the 9 volts out of this little tiny box here. The 9-volt batteries, they produce more voltage, but they don't last very long because the batteries are really, really tiny. Okay, I think that's about all we have on this part of it. So what we'll do now is we'll go back into the rest of the class and talk about some of these other things. So that's basically what electricity is. It's where it comes from, how we make it, and these are just a few things we can do with it. It's unlimited what we can do with electricity. I mean, everything, if you think about the lights we have, the radios, our cars, the televisions, all that stuff, it all runs off of electricity. And that's how we make it. Okay.
Okay. So that's kind of an introduction of what electricity is, where it comes from, and just a few of the things that we can do with it. Of course, in today's world, it's actually pretty much unlimited. There's so many things from electricity now that it's amazing. Okay, you're probably familiar with this if you remember back in your high school days. It's the periodic table of elements. And if you've ever studied chemistry or anything, these elements, each one of them, and I don't know the names of all of them, but with each element, there's a number. See that number right there? Okay, that is the atomic weight of that particular element. And what that tells you is how many electrons each atom has in that element. So this one has 21 electrons. And if you go down here farther, this one has 76 electrons. And you can come down here, this is 113 electrons in each atom. Goes all the way up to 118. Okay, now the smaller the number is, the less conductivity that element has. If you go all the way down to the bottom, or up to the very beginning, is hydrogen. It is the smallest and lightest weight of all of them, and it only has 1 electron. And hydrogen will not conduct at all. It will not conduct electricity. The atoms have only one electron and they will not give them up. So hydrogen is probably the most perfect insulator there is. Of course, it's a gas, which doesn't do much for you. But as you go up here a little bit farther, you get into some of the common things, you know, just 70s, 80s, 90s. And these are not real good conductors. But if you get up into this bottom row here, you're getting into lead and zinc and copper and gold and silver and all of those kind of metals. They have a lot of electrons on their in each of the atoms. And so these make really, really good conductors. They conduct electricity very well. So like I say, the more electrons that an atom has, the better it conducts electricity. It's kind of almost like having a lot of children in your family. The bigger the family, the more children you have, the easier it is to lose one of them. Well, it's kind of the same principle. You know, if you only have one child, not a chance you're going to lose that one. But if you have 8 or 10, one could get lost. But the electrons are kind of the same way, or the atoms are kind of the same way. When they have a lot of electrons, it's really easy to get one of them to move. So that's kind of determines. If you ever wonder, you know, what kind of a conductor something is, just look it up on the periodic tables, and the size of the weight will tell you what kind of conductor it is. Okay, we already talked about DC power, AC power, and frequency. And as I mentioned in the video, anytime you have AC power, AC current, there's always a frequency. It's how many times per second it goes back and forth. You know, this frequency can get up very, very high once we start getting into broadcasting radios and transmitting over the air. You know, the frequencies can be up in the kilohertz, the thousands of cycles per second, megahertz or millions of times per second, or even gigahertz, which is billions. But that's the frequency is just how many times that alternating current is going back and forth. Oh, we already did this. Okay, this is a picture of an actual commercial generator. And as you can see, these things are huge. They're monstrous. And you know, they probably weigh many, many tons. But inside this generator, this one's actually laying horizontally, which is this one right here. There's miles and miles and miles of wire wrapped around inside there, and a huge magnet. That magnet probably weighs 2 tons. And it's attached to something that's causing the generator to turn. In commercial world, there's a lot of different means of generating electricity. Water is one of them. Steam can be used for generating electricity, natural gas, and even solar. Well, solar is a little bit different, but we can use solar power or wind turbines. Just anything to cause the generator to turn, that will generate electricity. And here, this is an outdoor version of it. Looks like this one might be steam powered. You can see the steam here in the background. But this one's partially underground. But again, it's just miles and miles of wire wrapped around here. And inside, there's a huge magnet that's spinning, it's rotating. And whatever means they're using to turn that magnet, it just generates electricity. If any of you live in Kootenai County here, where we are, out on the prairie, there's a big gas-powered generator. You can see the steam coming up from it in the cold winter months. But that's just one of the means. There's lots of different ways of generating it. It's just you know, what's most practical and what's the easiest to do. Okay, one other thing I wanted to mention. For years and years and years, there's been a lot of controversy over the direction of electron flow. Whether the electrons flow from negative to positive or whether they flow from positive to negative. From people who grew up in the vacuum tube era, the only way that you can explain how a vacuum tube works is if current flows from negative to positive. That's the only way you can explain it. But in the newer world with solid state and the modern technology, the only way you can explain it is if the current flows from positive to negative. So we've had for years this disagreement over whether it flows from positive to negative or negative to positive. And the truth of the matter is nobody really knows. They've never been able to prove what direction the electrons actually flow. So what they finally came up with, just to satisfy everybody, is they took something like this, and let's assume that the electrons are flowing from out of here and they're going in this direction. Well, as the electrons hop from one atom to another, and then it hops to the next one and hops to the next one. So when it hops over to here, it leaves a hole over here. And then, of course, this electron then hops and fills the hole, and the hole moves up to here. So as the electrons are moving this way, the hole that's left behind moves this direction. So they came up with the idea, well, we'll have electron flow, or we can have hole flow. You know, hole meaning like a hole in the ground. So the actual hole that's left behind goes in the opposite direction. So that kind of satisfied everybody for a while, but there are still people who will argue the issue of whether it goes from positive to negative or negative to positive. But in truth, no one really knows. No one's ever been able to prove what direction the electrons actually flow. Because the electrons, even if you have an electron microscope, and if you're able to see the electrons, they're spinning at the speed of light, 300 million meters per second. And you can't even see the movement. When they actually move, you can't see it. There's no way to detect it. So we just have to go on a theory. But generally speaking, in modern day technology and solid states and transistors and so forth, it's pretty much accepted that current flows from positive to negative. And the only reason we have that is because that's the easiest way to explain it. But no one can prove it. Okay, so that kind of wraps it up for tonight. That's about electricity and where it comes from, what we can do with it, and so forth. So this kind of lays the foundation for what we're going to get into next week. Because there's actually, and I'm going to kind of forewarn you, there's a little bit of math involved, because we can actually calculate current, voltage, resistance, and all that kind of stuff. You know, if we know some of it, we can calculate the rest of it. So we're going to learn how to do that next week. Now, if you would like to bring a calculator with you, you can do that. And you can take a calculator when you go to take the test, but it can only be a calculator. You cannot use the calculator on your cell phone or a tablet or a computer. It cannot be associated with any other device. It has to be just a calculator and nothing but a calculator. So if you don't have one, you can go down to the dollar store and get a little cheapy $2 calculator. Those work just fine. The only math we're going to get into next week is going to be just the basic add, subtract, multiply, and divide. For those that want to advance and get into really deep into it, you can get into calculus and trigonometry and all kinds of that good stuff. It can get really deep. But for our purposes in this class, just the 4 basics: add, subtract, multiply, and divide. So if you'd like to come prepared with that next week, we are going to do a little bit of math. We're going to learn kind of how that works and show you some of the test questions that evolve around that. So I think that's about all we have for tonight. Any questions, any thoughts?
To read chapter 8.
Oh, yes. I'm sorry, I quit too soon. There's more. Oops. Come on. There we go. Okay, so your homework assignment, first of all, I would like for you to take another practice test. I know some people are kind of hesitant to say, well, no, I'm not quite ready for that. But the practice test will help you learn. You can learn a lot just from doing the practice tests. I've had some people, they'll take the practice test 2 or 3 or 4 times every week. And by the time the class is done, they've got it nailed. So if you would, there's a number of places where you can do it. This particular one is a website, qrz.com. It's a ham radio website. They have practice tests there. Or if you want to go to that one I mentioned last week, that hamstudy.org, there's practice tests on there. The hamstudy.org probably has a lot more options for you. They have flashcards. They have all kinds of cool stuff on there for learning. But I do want you to take a practice test, at least one. And if you want to do 2 or 3, that'd be great. And then in addition to that, the reading assignment for next week is going to be chapter 8. That's Operation Regulations. And if you remember last week, I told you we're starting at the bottom and working our way up. So you're going to be reading about the rules and regulations. And that's actually going to be the biggest part of the test. So make sure that you go over that pretty good. And I'm not going to cover much of it in class, but if you have any questions, please bring them to class. I'd be more than happy to answer any questions you might have. And as you can see, the chapters 2, 3, and 4, that's all the technical stuff, which we're going to go over in class. Okay. And you don't have to turn anything in for your homework assignment. It's just you're grading basically on how you're doing on the practice tests. And at this point, if you can get 25% on the practice test, then you're okay. You're right where you should be. And if you don't know the answer, guess at it. Just take a wild guess, and you'd be surprised. Sometimes you might be able to get it. So if you do those 2 things this coming week, and then next week we'll go over some more things after that. Okay, there. Now we're at the end of it.
Question, Dale.
Yes.
So is there one particular practice test that that just shows the correct answer? You know, it may be in bold and the other ones are under intensified.
Well, actually, I think I sent out the question pools last week. On there, it has those are the 600 questions that your test will come from. They are the exact same questions. And what I tell people is go in, because at the top it tells you what the correct answer is. So take a marking pen and just mark out all the incorrect answers, so that when you read it, you read the question and only read the correct answer. That way it kind of sticks in your mind and it's familiar to you. But as far as actually taking the test, no, there's no clue as to which one's the correct answer. They keep it pretty flat and pretty simple.
Okay, thanks.
Okay. Any other
Hey,
questions?
Dale, don't forget to stop the recording.
Okay, thank you. I'm glad you guys remember this because I tend to forget. Okay, so